Your body doesn't panic when food disappears. It's been waiting for this moment for 300,000 years. Somewhere around day 2 without food, something switches on. A survival mode so effective, it might be the reason you're alive to read this at all. Let's walk through it from the very first hour by hour. The sequence is more precise than almost anyone assumes. For the first several hours after your last meal, your body runs on the simplest fuel available. Glucose circulating in your blood, topped up by glycogen, a stored form of sugar packed into your liver and muscles like a savings account for exactly this situation. That account isn't very large at all, not compared to what's coming next. Roughly 12 to 24 hours in, most people have burned through the bulk of their liver glycogen. Blood sugar dips. Insulin, the hormone that tells your body to store energy, drops sharply. There's nothing left worth storing. As insulin falls, a second hormone rises to take over. Glucagon, insulin's counterpart, signals the liver to manufacture new glucose from non-carbohydrate sources, amino acids, fat byproducts, through a process called gluconeogenesis. It's the body's improvised workaround, cobbling together fuel from spare parts while the bigger system gets ready to take over. A stopgap measure only. Buying time before the body commits to something bigger. This is where the real shift begins. With glycogen running low, your body needs a new fuel source. It has one standing by: fat. Your liver starts breaking fatty acids down into molecules called ketone bodies, a completely different fuel your brain and muscles can burn instead of glucose. Even a lean person carries enough stored fat to theoretically fuel weeks of basic energy needs, far more reserve capacity than glycogen ever offered. Fat is dense, stable, easy to store long-term. That's probably exactly why evolution built the backup system around it. Somewhere around day 2 or 3, this process, ketosis, ramps up fully. Your brain, an organ that normally insists on glucose and almost nothing else, starts drawing a significant portion of its energy from ketones instead. This finding predates the word ketosis by decades. In the 1960s, physician George Cahill ran a series of studies tracking exactly what fuel the brain used during extended fasting, using volunteers who fasted for weeks under close medical observation, while researchers sampled their blood repeatedly. What he found broke the accepted wisdom of the time completely. The brain, believed to require a constant, uninterrupted glucose supply, was perfectly capable of running largely on ketones instead, once given enough time to adapt. By roughly the 3rd week of Cahill's fasting studies, ketones were supplying close to 2/3 of the brain's total energy needs. With the remainder still covered by the small trickle of glucose the liver kept manufacturing through gluconeogenesis. A figure that stunned physiologists who assumed the brain simply couldn't function that way. Your body wasn't improvising. It was executing a plan tested over and over, across an enormous number of ancestors who occasionally had nothing to eat for days at a stretch. Here's where it gets stranger, though. Because ketosis isn't the only major system switching on, deep inside your cells, something else activates during extended fasting, a process called autophagy, literally self-eating. Individual cells begin breaking down and recycling their own damaged or unnecessary components, old proteins, worn-out cellular machinery, material that's been quietly accumulating and cluttering the system. This isn't a metaphor for cleanup. It's literal cellular recycling, and it earned a Nobel Prize. In 2016, biologist Yoshinori Osumi won the Nobel Prize in Physiology or Medicine for identifying the genetic mechanisms controlling autophagy. Working primarily with yeast cells in the 1990s, he identified more than a dozen specific genes essential to the process, then traced equivalent versions into human cells, confirming the same recycling machinery had been conserved across an enormous evolutionary distance. This wasn't a minor biological footnote. It was a fundamental, ancient mechanism, present in nearly every complex organism on Earth, running quietly in the background of essentially every cell you have. His research showed the process ramps up dramatically under nutrient scarcity, triggered by the same signal that tells your body food has stopped arriving. Cells that normally receive a steady stream of new building materials suddenly have to make do with what's already inside them, waste less, recycle more, an efficiency program that only makes sense to run when supplies are genuinely limited, but none of this is free. And the cost gets clearer the longer a fast continues. Your body works hard to protect muscle tissue during fasting through a process called protein sparing, prioritizing fat and ketones for fuel specifically to avoid burning muscle. Muscle is expensive to rebuild, in raw calories and in time. An ancestor who lost significant muscle mass every time food ran short would have been at a real disadvantage the moment hunting or gathering became possible again, slower, weaker, less capable exactly when capability mattered most. But the protection isn't perfect. It isn't unlimited. As a fast stretches past several days, some muscle breakdown becomes unavoidable. Core body temperature drops, blood pressure drops, heart rate slows as your body actively throttles itself to stretch whatever energy remains as far as biologically possible. This is documented in extensive and often unsettling detail in one of the most significant studies in nutrition science history. In 1944, physiologist Ansel Keys recruited 36 healthy young men, most of them conscientious objectors, who volunteered specifically to contribute to the war effort without fighting, for what became known as the Minnesota Starvation Experiment. Over 6 months, the men were placed on a severely restricted diet designed to simulate wartime famine, while researchers tracked every physical and psychological change in extraordinary detail, sometimes measuring participants multiple times in a single day. The physical findings were significant. Heart rate slowed, body temperatures dropped. Physical endurance collapsed to a fraction of baseline. The psychological findings were what genuinely shocked researchers. Participants became obsessed with food. Some collected recipe books despite having nothing to cook. They dreamed about meals, talked about meals, planned meals they had no intention or ability to make. Mood swings, irritability, and depression deepened as the study progressed. A few participants reportedly experienced psychological distress, severe enough that researchers had to intervene directly for their safety. Keys documented a specific pattern of psychological deterioration that researchers still reference today when studying the mental effects of severe caloric restriction. Extended fasting was never purely a physical event. It reshapes behavior and mood in ways that surprised even the researchers running the study deliberately, under controlled conditions, with full medical supervision. That last detail matters more than it might seem. The Minnesota study documented something else too, something that stays critically relevant today. The danger isn't just the fast, it's coming back from it. Reintroducing food too quickly after extended fasting can trigger refeeding syndrome, a potentially serious shift in electrolytes, phosphate, potassium, magnesium, as the body suddenly restarts insulin production and processes it had slowed to conserve energy. The body, so carefully throttled down to survive scarcity, can struggle badly with the shock of abundance arriving all at once. In severe cases, this shift can affect heart function directly and requires careful medical management to navigate safely. This is precisely why extended fasting, historically and today, has always required medical oversight. Going in, and especially coming back out, the system that gets you through the fast was never automatically equipped to bring you back out of it safely on its own. So what actually happens to your body across a week without food isn't a slow decline into pure crisis. It's a structured, sequenced series of switches: glycogen depletion, the shift into ketosis, a surge in cellular cleanup through autophagy. A whole body slowdown designed to stretch limited resources as far as biologically possible. Each phase has its own timeline, its own hormonal signals, its own specific purpose, layered on top of the one before it, like a series of contingency plans your body only reaches for once the earlier, simpler options have already run out. None of it was designed for the modern world. It was built, tested, and refined across hundreds of thousands of years by ancestors who regularly faced days, sometimes weeks, without anything to eat at all. Every single one of them survived long enough to have children, which means every single system described here, glycogen, ketosis, autophagy, protein sparing, passed the only test that has ever actually mattered. You inherited a survival system engineered under genuine scarcity, still fully installed, still ready to switch on the moment it's needed, whether or not the world around you ever actually requires it anymore.